Okay, so we're going to get into these problems. Basically, they're all very similar to each other. You just have to be careful that if it says double slit, you go to the double slit equation, and single slit is the single slit, and then diffraction is the diffraction equation. Although the diffraction equation is exactly the same as the double slit equation. Okay, so we'll just jump in here and see how we're doing these. So I'm going to draw the diagram at the bottom of the example so I can refer here to it. I'm going to simplify it a little bit. So here's the wall. There's the two slits. This D, this little D, is this distance between the slits. Okay. Now, as this happens, what this is going to do is um, right in the middle. Okay. I'm going to draw this on the other side, but you're going to have a maximum right in the middle, and then it's going to fall off and then back up and fall off and back up and so on. Okay. Now, what this theta, I should have drawn this bigger, but if you draw a line straight across, and then you draw a line to where, now it's not going to be back here, it's going to be right on the screen where it happens, and it's not going to match up here, but this theta then will correspond to a maximum, not the minimum there. Okay. M is basically how many you're away from the middle. So you could put 0 for M, first order. If you did another one, it would be second order. So M1, M is 2, M is 3, and so on. Okay, so we call that the order. And then lambda is just the wavelength. Now you have a wavelength. Let me write the equation so I can refer to it. So sine of theta is m lambda over d. Relates all this stuff together. M, you kind of have to be told. Lambda is the wavelength. Now you have a distance and a distance. So those distances have to be in the same units. I always just say convert both to meters. If this is millimeters, d, you could try to convert nanometers. Usually invisible, that's going to be nanometers. But that's a little tricky. So I just convert all to meters. Um, so without even following the derivation or anything, this is the equation for double slit. Okay. So for this one, for this example, and we're told, okay, millimeters. The slits are 0.1 millimeters apart. Okay. Now we're also told this distance here from the slits to the screen. That doesn't appear in this equation, okay? Because you can give the distances here in two ways. You can give the angular distance just by theta, or you can give, an actual, which on the triangle here would be this. I'll just call it x, which is a linear distance on the screen itself. It just depends on what the problem asks for. That involves an extra step. Okay. Let's see. We have 500 nanometer wavelength. So if we're converting these both to meters, this is millimeters, so this is going to be times, let's see, millimeters to meters, so this is times 10 to the negative 3 meters per millimeter. This one's times 10 to the negative 9th meters per nanometer. So when I do this, I literally just, I don't try to mess with this. I just say, D is 0.1 times 10 to the negative 3. Lambda is 500 times 10 to the negative 9th. Don't make this like 500, like 5 times 10 to the negative 7th. You can if you want, but. And for this problem, we're asking for adjacent. Okay, so from 0 to 1, that means we want to find for order 1. always going to be an inverse sine here. Let's see, 1. There's no units on that. So we're just plugging in everything. Now, this can be in degrees or radians if you want, but so we'll just get okay. So now this is 0.286 degrees. Now, as usual, I see these examples and I just start going. So that's fine as a calculation, but let's step back from that. Okay, so let's take it. We filled everything in right. Okay, now I'm gonna use radians. And, okay. And I'll explain why in a second, because this problem, it has a little bit of a different end here. Okay, so it could have said find the angle, and you could find the angle what we had there, fine. But if we want the distance, now to simplify this, this is a very small angle, so we're going to use a small angle approximation. I'm not going to write that out. Where we say, well, we can say several things. This can say, and this is only if it's in radians, that the sine of theta, or we'll put it this way, and we use this as approximately theta. You can also say tangent of theta is approximately theta. You can also say, now what that means, I'm getting into too much detail here, but what that means is that since like if we call this L, this 1.2, then when you get very small, then that's basically L2. And then X we can approximate, even though X is a curve, we can approximate that as a straight line. So we can say that, go back down here, we can use what we're going to use for this problem and say that X equals L theta. Okay, that's our theta. L is the 1.2, so just plug that in and get your answer. I'll leave that up here for a second. This guy right here. Now we could have used, because they told us the L, we could have not used the approximation, but okay. And if you look at the homework hints file for this chapter, there's a few problems where we use that in the homework. Okay, 24.3. Now this is still double slit. Okay, so now we have white light passes through two slits 0.5 millimeters apart. I'm just going to go ahead and write this stuff down as I see it. So again, I can write this down just straight like that. 0.5 10 to the negative third. Okay, interference patterns observed on our screen 2.5. So I'm going to go ahead and say that L. That's my screen distance. Okay, the first order fringes. Okay, so we get a rainbow effect. The violet light is 2 millimeters, and the red is 3.5 millimeters from the center. Okay, so we're going to do this twice, once for red and once for violet, just estimating the wavelengths. Okay, now let's see what other information we have. First of all, again, M is 1. What do we have? We have, let's just do violet first. We actually have that X variable. Okay. Sorry, times. So look back at the previous one and see that X variable was the linear distance on the screen, and we have L. Okay, so that means if we have that same small angle approximation, right? So we can find for theta first, x over L. I'm going to write this out, 0.0004 radians. Now that's not our answer yet. Okay, we want to find lambda, so the wavelength. So lambda, again from the same equation, is going to be d sine theta over m. Where again, we can just plug this directly in. You could take the sine of 0.0. Let's try that and just see how different it is. So if I'm in radians and I do sine of 0.0004, look how close that is. You can see that. I mean, it's 1 part out of a million or something that we're away. Okay. So we can say this is basically equal or approximately equal to d theta over m. Okay, and then you have d here. You have theta, m is 1, and your answer will come out in meters. Okay, so repeat that for the only difference with red light is x is going to be different. That's it. Okay. 24.5. Okay, now we're going to move into single slit. I'm not going to go through all the derivations, but it's different. It's a little bit fundamentally different because if I write the equation here, it's very similar, but sine theta equals lambda over capital D. Okay, where D is now a single slit. We need to know how wide it is. Okay, and that's it. Now we're not looking for a maximum. Okay, but what this tells us is where the where the light comes through to a minimum. Okay, so if I kind of draw this out here, actually, if I can get my book over here, that would be easier. Let's move the let's see if I can get my book over here. Okay. Okay, so this is the single slit. Light comes in, single slit, and you have this sort of central maximum. Okay, now that's not all the light. If we look up here, okay, but you can see most of the light is in this central maximum, and then there's a secondary maximum, okay, and a third. In fact, I left m out of that equation. I should put that in. Okay, so where's m going to be? M lambda. But most of the time you'll see that m equals 1 for this problem as well. Okay, so let me get to the solution here. Okay, so for this problem we have, let's see, light. We know the wavelength here. You see, we're all dealing with visible light, which is in this 400 to 800 or so nanometer range. I guess I can go ahead and put this times 10 to the negative 9th meters. And the slit width here is actually 1 millimeter. How wide is the central maximum? A in degrees and B in centimeters on a screen 20 centimeters away. Well, can't use the small angle because you saw on the diagram these angles. For this one, we're going to get an answer of 49 degrees, so you can't use the small angle for this, but we don't need to. So let's see, inverse sine of m, so that's 1. I'm going to run out of room there. Inverse sine 1 lambda divided by d. I'm going to trust that that comes out as 49 degrees. Okay, now that's up and down, so the entire width is double that. Okay, so width equals 2 theta, or 98 degrees. Okay, so that's the answer to part A. Now, to get the answer to part B, basically, you have this setup where you have, we can just call it x again, and L, and theta. And so that's just tangent, right? So tangent theta is x over L. So you can find x, that's what we want. So x equals L tangent theta. And of course the full width is 2x. So we want 2x is going to be 2. That's why I wrote that 2 there. I think 2 tangent theta. Okay, I'll let you complete that on your own. And one more here. We have one more type, that's the diffraction grating, which it's only different words. The equation is the same as the double slit. Diffraction grating has a little bit different a pattern. The maxima are very tall and the minima are very small, so you concentrate light but out in the different maxima as you go out. But mechanically as we do the problems it's the same. So 24/7. So we got, determine the angular positions of the first and second order lines maxima for the light wavelength 400 nanometers and 700 nanometers instant on the grating. Okay, so one of the differences, this D, sometimes it's given in this is still just a distance, but for example, for this problem we have 10,000 slits or lines per centimeter, but we need centimeters per slit or line. Okay, to do that you take the inverse, so take 1 over, so D, and this will be in centimeters. I'll do it on the calculator, but so 10,000, where's my inverse button? I don't use it very much. Inverse. Or you could just do 1 over 10,000. So 1 times 10 to the negative 4th centimeters. So it's also times 10 to the negative 2 for meters. So 1 times 10 to the negative 6 meters. That's D. You have to do that in a few of the homework problems, so don't think, just skip that part. Your answer will come out, with wrong powers of 10. Okay, and we're told, I'm just going to do this for one wavelength, and then you just repeat it for the different numbers, but let's just do this for 400. That's the violet, again, times 10 to the negative 9th meters. What else do we need? Well, determine the angular positions of the first and second order. So you're going to do, for 400, you're going to do first m equals 1 and then m equals 2. And then for 700 nanometers, you'll do 1 and then 2 again. So they're actually asking for four solutions here. What do we want to find? Well, angular position means the angle. Okay, and again, we're not talking about a small angle here necessarily, so so we'll do 1 first. So I think it's every problem in this chapter is basic. Oh, you missed that. Okay, so I just wrote that out there. It is basically very similar in construction. You just have to get the details right. Use the right equation. Okay, pick the right m, and so on. Know when to use the small angle. Which, if you don't know it, if you don't know if you can use it or not, you probably can't not use it. Okay. I think I put something in wrong here. Yeah, I put 10, so this would actually be just 0.4. And that's good enough. That's radians. Is that radians? That's degrees. No, I'm in radians. Well, that's radians if you want to give your answer in radians. Um, or we can redo the same thing and get 2.29 degrees. I'm trying to see where they just give the answer, and I cannot see where they're putting the answers here. I get 23.6. Because I used that 0.4 from before, I think. Yeah. All right. Well, we'll get there eventually. I never think physics, anybody can just breeze through the whole thing without, having to backtrack. There's your 23. Okay, so that's, ignore all that. This is 23.6 degrees. Okay, and now you would just repeat for 700 and then do 400 with 2 and 700 with 2. And okay, let's see, that's it. Okay, I'll stop.